So, anyways, obviously Blackboard has all everybody's exams. That's where I keep, what I use Blackboard for is just like, oh look, I grade, and I submit your grades there. Don't let it do your, students will go, it's like, oh, my calculations are, don't. Blackboard make calculations. It's like, if this is your exam 1 grade and this is your exam 2 grade, everybody should be able to do algebra to calculate your weighted average and things like that. That's where I keep that. For exam 1, probably the average, not probably, the average was 77. So the average was 77%. The median was about, I think, 78%, which tells me that basically it really wasn't useful if you guys can see it. There we go. So average and median, if those are greatly divergent, that usually tells me that the class is strongly bimodal. This wasn't. I think the high was like 101 was the max out of this one for everybody's classes. So it's honestly, it's where I expected. That's, in terms of things, where people get them wrong is where they get them wrong. I think that whole, threatening anger, about square root of 2 is irrational did pretty well. I got it down to 2 blanks, so about a 70 out of 85. So that's doing a lot better for me. One of the things, again, if you look at it, there should be essentially no surprises. So when we say things like, if I said things to work on would be, if I said A is, say, necessary yet not sufficient for B, right? I would say something like that. Anybody remember that from the homework? Except they use the word and. Okay, if I would leave off the whole, if I would leave that off, if I would simply say A is necessary for B, what's that? B implies A. If I would say A is sufficient for B, then you would say A implies B. But if I would say that's not true, right? Then really what this was is A is necessary means B implies A. That's A is necessary. Yet is actually an and. It is not true that it's sufficient, so A implies B. Everybody remember that one from the homework? This is probably one of the most missed problems. A lot of people did just simply, one of them. And when, on that 2-part problem for A, for part 2, if you did that wrong, but you did the truth table on what you did wrong, that's fine, right? Because I asked for a truth table for what you did. I'm not like, oh, look, because you got that wrong, I'll give you more points wrong. No, you had to, you just did a truth table. So again, if you look at these, a lot of these as they go through, it doesn't seem familiar. And I'm not going to give you things that are completely out of whack. They're going to be based on stuff that we did in class. Everybody remember me doing this in class? Right? There'll be ones that we did in class, you asked questions about, there'll be nothing that will be like, I have no idea where that came from. Another one common mistake was if I would say things like use logical equivalencies, and we had that whole P and Q implies P, right? Using logical equivalencies is use logical equivalencies. This is, for example, logically equivalent to not P and Q or P, right? You don't have to say what you did, which is I used the disjunctive form. And then that would be not P or not Q or P. I used De Morgan's, right? That's just simply not P or not Q, right? That's associative and commutative. And that's true or not Q, which is the negation law, right? Which is true, which is the domination, right? When I said use logical equivalencies, which is, and they're never going to be ones that are more obscure. You can just simply go through and use the ones that pretty much everybody should know. So, other ones, as in terms of the exam, I'll hand them out next class. One of the things that you should do, and this is kind of important, is how do you study for the final? Okay, the way I make my final is I'm going to take, including the extra credits, I'm going to take 11 problems from exam 1, the 11 problems from exam 2, the 11 problems from exam 3, the 11 problems from exam 4. I will have 44 problems. And then I'm going to go through that and start throwing things away until I get to, I think on the final I'm going to do 16. I'm going to start throwing things away until I get down to 16 problems. And then I'm going to start tweaking every single one of those. Certain ones will be, I'll say on later, you're going to have to be able to either prove that the rationals are countable or that the reals are uncountable on this exam. So let's say I pick one. But that means on the final, I might pick the opposite, right? I could say, all right, in exam 4, I had you prove, actually exam 2. Exam 2, I had you prove that the rationals are countable, but maybe on the final, I'll go ahead and pick the reals are uncountable, since I said you had to know either one of those, right? And so that's how you study for the final, is you study for the exams. In other words, when you get these things back on Monday, you have your grades now, but when you get these handed back, do not accept what you cannot do. Oh, I can't do that. No, that means don't put away it. That means you should be able to take exam 1, fix it in its entirety, make up new problems based on every one of those problems, and find somebody else in this class to study with and say, hey, look, here's my exam 1. Why don't you do that for your exam 1, and then both of you do the other person's exam that you make up for fun. And if you do that, you're ready for the final, right? That means you can do all those problems. Anyways. Questions? Whatever the calendar says. I'd have to look at the calendar. I think, well, that's true. This class, I think, has the final like on the Wednesday of finals week at like 8 a.m. And then an hour from now, after this one, the 10:30 class is supposed to have their final like on Friday at 10 a.m. You know, like, and what I'm probably going to do is going to see if I can actually schedule just one day. The hard part is those are scheduled that way so that we don't have conflicts, right? But it'd be nice if I could have just all of them on Wednesday, or I'll have to ask people, will this conflict if I do this? And I'll schedule like a really big lecture hall and have all 85 students show up. And see. That way, instead of having 3 different times where people can take a final. So, yes?
Now, I know you mentioned the notation of Venn diagrams last time, that you should put the capital letter on the outside of the circle.
You put it on the inside or on it.
The book had it all inside, and I wasn't sure whether...
That's when you type on it and stuff like that. The issue when you do, just for, like when you're doing things by hand, like this, you know, if you say things like A and B, it should basically be at a place that you know what the circle is implying, right? So if you put it on the inside, a lot of times we'll be having problems where you put things on the inside and you write it as an element. Well, maybe the elements happen to be the capital alphabets.
So just so it's clear.
Just so it's clear. That's one of the reasons why a lot of people will go ahead and just simply break, you know, a part of it and then write B like that. Then it's very clear that, oh, I can tell in my mind that that's B because I wrote it literally on top of the circle. And then there's kind of like no question on where it's at. So you just have to be careful as you do those sorts of problems. So where you write that, as long as we all understand, we're good. Unless it's like nobody's ever seen that notation before. Then you have to define it. This is my notation. And you'll get that, honestly. I mean, how many discrete books are there? Go to the library. You know, there's tons of authors. There's tons of authors that have done set theory. Everybody picks their own notation. You just have to say, I'm going to agree with what the author does. Or if you read another book, a lot of times you have to stop and spend a lot of time figuring out their notation before you can move on. So, extra credit. I guess another one is this. The extra credit is online. In other words, when we look at, if you go to that whole chaos math, which I use /321, or just there, it has a link to it. These are all here. And so square root 2 is irrational is the one you're going to prove by the week of exam 2. And I mean by the week, sometime around there. I've already had 5 people already stop by and prove this. You get points, right? You do all of these, if you did them all, it would raise a letter grade by a half point, right, by the end of the semester. I did everything, and I'm making a 80. I took well, hopefully did it before all this point, but up to the final, you made an 88. That means if you sat down and did every single one of these, it would lift it up a half letter grade, so your B plus goes up to an A, right, if you choose to do this. But that doesn't mean that you show up after, like the week of the finals and say, can I do them all? I need it. But no, because I can't grade that much. I don't have enough time. So that's why I break it out earlier. We're going to prove, if you'll notice a lot of these, for example, the square root 2 is irrational. That was on the exam. You are either going to do 1 or 2 on the next exam. I will say you're going to do a proof of countability. You're either going to do that the rational numbers are countable or the real numbers are uncountable, one of them. But you should be able to do both. 3 is not in the text anywhere. All right, I'll talk about, when we do number theory, I'll talk about the figurate numbers and what does it mean to be a geometric shape. And from there, you can actually geometrically show certain things. The proof of the cubes, this third one, we will prove those 3 using induction. We will prove those 3 using the way Gauss did it as a child. But I want you to be able to also do it geometrically. There's geometric interpretations. The geometric shapes of the third is kind of an old classic one from thousands of years ago. And it's a shape that the sum of k cubed is equal to, and there's a formula, and that formula is a shape. It's a geometric shape, which is kind of interesting. And then obviously we have counting problems. If it's the fundamental theorem of arithmetic, you should be able to prove that. That's actually, fundamental theorem of arithmetic is a combination of 2 proofs required in the course that are done chapters away from each other. One uses induction, and one is talking about the ideas of existence, that you can actually factor things by their primes. Infinite many primes, that's another classic. Pascal's identity, that uses that Pascal's triangle, proves why it works, type of thing. So, in other ones, that's a counting problem, which is kind of interesting just to do it. So some of these you won't see in the book. You will have some background on how to do it. It's up to you. I don't know how to do that. You can stop by and ask questions, and we can go through it. So, all right, that's the extra credits that you guys can do.
1 point?
5 points for all of them. So let's say you did 9 out of 9. That's 5 points towards your entire grade GPA type of thing. You did half of them. Well, you can't do exactly half because there's 9. 9's not divisible by 2. But you get the ratio of it, right? We'll talk about divisibility when we do number theory. All right. Sets and operations on the sets. So we stopped on comparisons last time. If we compare 2 sets A and B, the first thing we talked about was A is a subset of B. What does that mean logically?
For all elements, the element belongs in A implies the element belongs in B.
Okay. What about a proper subset?
For all E belongs to A, then E belongs to B, and there exists an X that belongs in B, but does not belong in A.
That's a very appropriate use of but, right? It's and, but it's like I want to make a point that it's not in A. That was actually the most appropriate way of dealing with that word. So, and third, what does it mean to be equal? What's the only difference?
It can only get
It's biconditional, right? which actually ends up being subset, right, if we want to write it that way. All right, so those are the three compares we had. Then we also had a comparison on the question of size. Size, we use the idea of a bar on either side. This means cardinality. Cardinality of A. Cardinality of A, so when I look at A, this is equal to the number of distinct elements of A. It's kind of the important part. When we talk about equality, we had this issue of, well, what about distinctness? What if one has, 3 number 2s and the other one only has 20 number 2s? Are they the same? And the answer is yes. I don't care how many. I just ask about existence. And so a lot of times we'll just simply say, okay, fine. If how many doesn't matter, just existence, let's talk about existence, and we'll talk about the word distinct. Does it show up, and we only write it once? All right, if that's true, this introduces a new thing that always makes people scratch their heads. If the cardinality of a set is equal to n, which happens to be a natural number, for example, what's the cardinality of 1 square and triangle? Well, that's equal to 3. There's 3 distinct objects in it, right? Which happens to be a natural number, 0, 1, 2, etc. The cardinality of the null set is 0. It's the set that has nothing in it, right? Anything of this nature where you look at the distinct elements and you say, oh, I count them up and I get a natural number, 0, 1, up. Then, if this is true, we call a finite. A set is finite if you look at the distinct elements and you say, oh, look, it's a natural number. This now gives us finally the ability to talk about what does it mean to be infinite. And if this is not true, if the cardinality, if the number of distinct elements is not finite, A is called infinite. So now we have the definition for infinity. All right, what's the cardinality of, say, 1, 2, 3, ... right? That's not finite. So the double bar Z plus is infinite. That's what infinity means. It means not finite. That's it. So a lot of people think of like an object or like infinity. How do you think about it? Well, it's kind of an interesting question. Because if we would look at objects like this as really, if I wanted to, I could actually take things and make them a set of sets, right? If I would take, for example, the universe of discourse represents, this is all sets, right? And so I could go through here and have things like, well, for example, if A was equal to, say, 1, 2, and 10, right? And then I would go through here, and that's an element. And if I would make, a circle here, and this particular circle would represent the idea of this is the set of all finite sets, of which there's a lot. So for example, A's in there, right? That's equal to this whole 1, 2, 10, right? That's finite, so he's inside of it. So what does it mean to be infinite? Outside that collection. That's all it means. Right? The finite stuff is things that if I count their distinct elements, it's a number, right? That is countable. What does it mean to be infinite? Not that. It's outside that group. So everything out here are the ideas of infinity. So, for example, Z plus, that's an element outside of that is not finite. Out here is also things like double bar R. That's not finite, right? The real numbers. What else is out there? The rationals are out there, right? And now one of the things that we'll do, and eventually we'll have an interesting question, is for everybody that's outside, for all these things that are infinite, could I create new groups? Could I make a circle here and say, these are the not finites that behave like this? And then I'll make another group. Well, these are the not finites that behave like this. And so what I'll form is different types of infinity, things that are on the outside. And so that's when we talk about that one, some of those proofs. We're going to group certain ones, and we're going to call the guys in here, sure, they're infinite, but I'm going to call them countable. And then I'm going to take another group and say, well, these are not in that group, so they're not countable, and they're not finite, they're infinite, and they're a different type of group. And we'll actually look at these. And one of the things that's an open conjecture right now is that we have, it's essentially a partition, which is we'll have the finites, we'll have these types of infinities, which is distinct from these types of infinities, and they break out these clean, like room divisions. All these sets are either in the first or the second or the third. There's no crossovers. They're nice and clean and separate from one another. And it's an open conjecture on what it means to break up these non-finites, these infinities, in terms of countability. And when I talk about countable, really what we're talking about is, do they kind of act like the counting numbers? Right? I have 1, 2, 3, 4. It's not finite, but boy, it's well ordered, right? 1, 2, 3, 4. And it really gets down to, well, could I count the things? And are they countable or not? And then the answer is either yes or no, and then we have different types of uncountable as we go up. So that's one of the things that we'll approach, is all the different types of the infinities. Can we study them as well? All right. And that all comes down to just simply cardinality. How about in terms of other thing outside of comparisons? What about ops that don't compare but rather make new sets? All right, the first type of operations that make new sets are going to be things that are not closed. In other words, what happens? Okay, the idea of a not closed operation is a set goes into the operation, kind of acts like a function, right? And out comes some sort of new set, not like old set. It's like it makes this whole new set that's completely different from what that old set was. You know, examples of that would be, say, the cross product. And sometimes what goes in is not a new set, but new sets. And so the cross product, for example, if I have set A and I have set B, I'm going to make a new set that's called the cross product A cross B. And A cross B is a set, but what I do is A has elements, B has elements, and then from A cross B, I'm going to take one element from each. So my new object is going to be an ordered pair. What do these ordered pairs look like? Well, I have taken A out of A and I've taken B out of B. So example, what if A was equal to 1 and 2, and let's say B was equal to A, B, and C. So one set has numbers, one set has letters. What's going to be A cross B? It's going to be sets of all ordered pairs. I could take 1, then I could take A. I could take 1, then I could take B. I could take 1, then I could take C. Or I could have taken 2 and then A. I could have taken 2 and then B. I could have taken 2 and then C. Right? 6 things, 6 ordered pairs. One way of looking at a cross product, if you look at this, even though it kind of look at, like here's A and here's B, if I write 1, 2, and A, B, C, right? This is actually a spreadsheet. 1 to A, that's, oh look, 1A. 1B, oh there's 1B, right? It's a spreadsheet, that's all this is. It's like, oh look, if I have this many rows and this many columns, how many possible ways can I do an ordered pair? And that's my cross product. Obviously we can take this and go up, right? Instead of having just cross 2 things, we could generalize this and say, well, what about A1 cross A2 cross everything up to AN? Well, now it's not going to be, we'll have, say, little a1, little a2, up to little an, such that the a sub i's are element of a sub i's, right? This is an ordered n tuple. There's two of them, it's called a pair. If it's three of them, it's called an ordered triple. From that point on, we don't like to say quadruple or say anything. Just say n tuple. Oh look, I need 10. It's an ordered 10 tuple. And if I would look at this, we could actually talk about the cardinality of it. How many are there? If you'd ever want to count this, how many are there in A1 cross, A2 cross, everything up to AN? Well, it's just simply, well, how many A1s are there times how many A2s are there times how many ANs are there? Remember that whole spreadsheet? This is calculating what? An n-dimensional volume. Because area is, oh look, there's 15 rows and 14 columns. How many elements do you have? Oh, I don't know, 15 times 14. All right, well, what if there's 3 of them? Well, now we're doing a volume. Well, what if there's 4 of them? We're doing a hypervolume, if you want to call it that way. It's just a product. In terms of counting that particular, this rule that you see here is actually called the product rule. Because you product it, so it gets the product rule. So we can count on these, but obviously, is it making something very different than what you started off with? Of course, right? But it's still an operation. Sets go in and a new set comes out. Another one that we might want to do in terms of operations is, was I using A's? Yep, B. It's called the power set. The power set is written as P of S, which is going to be the collection of all subsets of set S. So I would take set S, did not know I did that. Oop. I would take set S and just simply ask, what are all of the subsets of him? And then just collect all of those as one large subset. All right, so example. If S is equal to AB and a square, what is the power set of S? Well, it's a set. And what goes inside of it? All subsets. Well, the easiest way to do this is just to simply say, if a set has 3 elements, making subsets is simply, you would go through this and ask, how many ways can I take no elements? Who's that? The empty set. And so these are all of the subsets, right, of no elements. How many ways can I take a single element? I could take A by itself, I could take B by itself, and I could take square by itself. That's the singletons. How many ways could I take 2 elements? I could have AB, I could have A square, and I could have B square. Those are all the duals. And then the last thing I could do is how many ways could I take 3 elements? A, B square, which would take the entire set, right? So how many subsets do I see? I had 8 of them. All right? And that's going to be true. The cardinality of the power set is always going to be 2 to the cardinality of the set.
So it's not, with the ordered pair, it's not like interchangeable as far as...
Because it's unordered,
Okay.
right? Subsets are sets, and sets are unordered. Now, on the other hand, the power set, the cross product is still a set, and they're unordered, but they're unordered ordered tuples. So, which is kind of fun, right? And so you look at the power set, and the power set is one of those really weird things as you start to build it up, and the book plays around like crazy because it's sets of sets, right? And then they do things like, ooh, I wonder what the power set of this is. Because like, okay, what's the power set of a power set? Oh, great. Why? Well, if this has 8 elements, right, and I took the power set of this, it'd be 2 to the 8th. And so I would have to make, right, 2, 4, 8, 16, 32, 64, 128, 256 elements. I would have to, how many ways to take nothing? Empty set. How many ways to take a singleton? Every one of those sets would be a new set all by itself. So you would have a set of the empty set. You would just have the set of the singleton A, the set of the singleton B set, right? And then you'd have duals. How many ways? Well, the empty set in A, the empty set in B, the empty set in the square, the empty, and then 256. And I don't want to do that. All right, why is it 2 to the power of S? Well, if we go back to kind of like a accounting question, when you're making subsets, right, if you count the possible subsets, you sit there and say that, well, when I do a subset, I either take the element or I don't. Every one of those, I have 2 choices, right? I'm either going to take that one or not. So what about A? I'm going to take it or not. What about B? I'm going to take it or not. What about C? I'm going to take it or not. So how did you do that? I either took A or not, and then I went to B and took it or not, and so it's 2 times 2 times 2. It's another cross product. It's a product rule. So, anyways, and so we know cardinalities. We have these operations. So these are the kind of the classic ones that we need to know that make something completely different from what I started off with. But we have reasons for it, right? Collecting all the subsets is a useful task. All right. 2.2 talks about these are going to be, what about set operations that stay in the universe of discourse? What does that mean? Well, that means this. I have one universe of discourse, I have a set, and I have a set, both of which exist within the same universe of discourse. And there's some elements here. And then, can I do operations on a single set? Right? And it makes a new set that's still in the universe of discourse. Right? That'd be a singleton operator, right? A unary operator. Well, could I take set A and set B and somehow combine them to make a new set that's still in my universe of discourse? Right? And so that's the sort of operations that we're going to do now. Closed operations. That I'm going to take sets that are within the same universe. I'm going to somehow jam them together in a particular way, and I'm going to get a new set based upon my old ones that still stay within my universe of discourse. So it'll just be certain other elements, right? The first of these we'll talk about will be the union, which is A union B. And again, operations should make sense. So if I had a universe of discourse I was talking about, students. Some of the students are math students, some of the students are computer science students. One of the things that might be useful for me to do it is just simply say, oh, let's take all of the math and CS students and invite them to the party. So let's put them together, right? And how would I do that logically? Well, what are all the elements in the universe of discourse so that the element is in A or the element is in B? So I'll use set builder notation, right? So what's the union? Take one or the other. Well, if I take one or the other, what would the Venn diagram look like of such a thing? If that's A and B, right? Elements in that region right there. That would be true or false. What's that? True. So it would be in the region. What about these points? True or true, and that is true, right? So that would be selected as well. What about this region? False or true, which is true, all right? What about this region? False or false, which is false, and so what does this return? That. That would be the Venn diagram of A union B. So that would be set that is set builder notation using logic, right? And then a Venn diagram. Second one, intersection. A intersect B is equal to, well, all elements such that the element is in A and the element is in B. What do you think the Venn diagram on that guy looks like? It's only true when they're both true. So that's their intersection, right, where they cross. We could do, I think the book even covers, it's not in the section, but it's in the homework. If we wanted to, let's do a 3. Let's do the exclusive OR, the XOR. What would be A, XOR B? It's all elements E such that E is in A, exclusive OR E is in B. What would that Venn diagram look like?
Union minus.
Right, it'd be the union, take away the intersection, right? I think it's that homework one. I mean, obviously we can keep building however we want, right? Like, for example, why would you want the intersection? Well, when are students, right? What about students that are both math and computer science? Why would you want the exclusive OR? I want pure math students and pure computer science students. I don't want any intersection right now, right? We would do something like that. We have reasons to work them out. That also would lead into the idea of a difference. What if I wanted to have A, but I want to take away the B's? Logically, what would that look like? That would look like all elements E such that I want the A's and I don't want the B's, right? But that also leads to a different one, which is a unary operator, which we call A complement, which is I want everybody that's not A. That also happens to be the universe minus A, if you want to write it that way. It's the entire universe of elements outside A, right? Get rid of the A's. If you want to, instead of using that like not an element of, you could rather use these are all elements, so it's not true that E is an element of A, if you want to write it that way. Those are the same thing. That's what that means. If you like the negation symbol, we could write it that way. Yep.
You could also use complement. So like for A minus
That is,
B.
this is complement.
But I mean, like, to integrate that into A minus B, E such that E.
Oh, like this
is
one?
A factor of A and E is a factor of complement B.
Right. Yep. Yep. And so you can actually play around with those, and that actually introduces different ways of writing it, right? And so logically, we could look at this and say, okay, kind of a little note. You know, sure, A minus B is made up of all elements E such that E is in A and E is not in B. I want to take out the B's. But somebody say, well, wait a second. That's logically equivalent to saying that E is in A and then and E is actually in B's complement. But and being in two things is actually saying that A is intersecting B's complement. And the answer is, yeah, those are the same. And so now we have ways of writing the notation. And then somebody else says, well, wait a second. I noticed that E in A, and it's not true that E is in B, but I like to use De Morgan's. And that's, okay, that's not true now that E is in is not in A, or E is in B. Right? Using a double negation to Morgan's thing. But to be not in something means that it's actually in its complement. And so that means, all right, so let me see. That's all E such that it's not true that E is in A's complement or E is in B. And negation means complement. And or is union. So that means this is actually A's complement union B's complement. Right? And you look at that and say, hey, look, it means the same thing. And the answer is, yeah. So all of a sudden we're looking at this, and what are we learning? We're learning ways to do manipulations of set-offs. And all of them, now, on the other hand, where did this all come from? What was I doing? From here to here to here. I was using set builder notation, but what's inside of set builder notation? Logic. So everything that I can do logically has a natural, oh, wait, that's a set operation. That's based upon that logic. And so all the logical equivalencies become logical equivalencies inside of the set builder becomes what I would call set identities. So example, A union B's complement is A's complement intersect B's complement is called De Morgan's set identity, which is De Morgan's law. But then A intersect B complement is A complement union B complement. And if you would look at this, you would ask, why? Why is it that A union B's all complement is actually A complement intersect B complement? Well, you'd sit there and say, okay, let's say I would take this first one. A union B complement is really what? This is all elements E such that it's not true that E is in A or E is in B. The complement says it's not this. Well, logic allows me to do what? I could use De Morgan's law. And so can you tell why we call it De Morgan's? If you logically use De Morgan's law, the set thing that comes out we will call De Morgan's. If I will use the associative property of sets on logic, I would call it the associative property of sets because I'm going to use the associative properties of logic. And that's just simply equal to all E such that it is not true that E is in A and it is not true that E is in B. But if you're not in A, what are you in? A's complement. And is actually intersection. So that's A's complement intersecting B's complement. So what we did is if you use De Morgan's, you call the thing De Morgan's. So this, on page 130, when you look at all these set tables, these set identities, we learn things like this. A union B is B union A, and this is called the commutative. Why do you think it's equal? If we called it commutative, what logical law applied to make this happen? Commutativity of logic, right? And how would you prove this? Okay, what is A union B? That's all elements E such that E is in A or E is in B. Well, or is commutative. That is E is in B or E is in A. Logic is commutative, therefore Sets are commutative under the or, under union. Because or is commutative, union is commutative. Because and is commutative, intersection is commutative. And so for every one of those, the identity, the domination, the idempotent, the domination's fun. Which is, say, what is A union everything you're talking about? Everything you're talking about, right? What is A intersecting the empty set? What do they share? Nothing. The empty set dominates. Why? Because under or, true dominates, and under and, false dominates. That's why this is true. And that's why we have the domination. You also have the identity laws, the things that do nothing. Idempotent, do it once. Associative, distributive, De Morgan's, absorption, complement. They're all there. All you have to do is use the logic, and that's where the set notation comes out of. All right. One of the things that we should note here is, what about Venn diagrams? And then I'm going to also talk about membership tables for 2 sets and 3 sets. And now comes a question of, could I go higher? We will only do 2 sets and 3 sets. All right, for a Venn diagram of 2 sets, a Venn diagram of 2 sets looks like this. It has 4 regions. A Venn diagram of 3 sets has 8 regions. So if this was A and B, and this was A, B, and C, these will always break up the space into 4 regions, which is in A not B, in A and B, in B not A, and in neither. The 3 regions have 8. In A, not B or C, in A and B yet not C, in A and C yet not B, in A, B, and C, in B but not AC, in BC but not A, in C but not AB, and in none. And you look at that and say, all right, this is, now what would happen if I went up to, all right, with 2 sets, I had 4 regions. With 3 sets, I had 8 regions. With 4 sets, I'm going to have how many? 16 regions. And so, oh, how do I best approach this? The way you best approach the regions is to use essentially a modification of the truth table. What you do is you say, okay, I have A and B, I have A, B, and C. And instead of saying true, false, I say in or out. And for 2, I could be in A. This, they use 1s and 0s. This is not really a 1 and a 0. It's an I and an O. You are in A, out of A, out of A. In B, out of B, in B, out of B. And in terms of rows, this is row 1, this is row 2, this is row 3, and that's row 4. And that's my row labels. Well, what about 3? In, out, 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 out. In, out, out, in, out, out. In, out, in, out, in, out. So first row, it's in all 3, right there. What's row 2? In A and B yet not C. That's that one. Row 3 is in A and C but not B. That's that one. Row 4 is in A but not the other 2. There's 4. Row 5 is not in A but it's in BC, which is right there. Row 6 is in B but not C, and 7 is here, and then 8 is there. from this point on, once we do this, we can actually do the logic that you normally do with truth tables becomes logic of membership tables. So if I would do compound operations like what is A union B complement intersect C, you would just simply make a membership table, and then if it's a 1 on its row, you would go to the number and color it in. So it's a color by number. And that's how this works out. And so it's nice. It also allows us to skip Venn diagrams. What if it's hard to draw Venn diagrams for 4 sets, 5 sets, and 6 sets, but membership tables are easy. And so it would tell me which regions. I don't know, I'm not going to draw them, I just can tell you which region it is. I don't have to eyeball it. It's fun. Go online to Google and try Venn diagrams for 4 sets, 5 sets, 6 sets, and they look crazy. They have all these really weird patterns. And they're like, what are Venn diagrams for prime numbers of sets? They have some really pretty pictures. So they look really strange. Anyways, so those are our ops. Attendance. Let's do example from 2.3 on page 142. Make you read ahead. Example number 10. Obviously it's done there, but make it your own. Make you read ahead. Sorry, that's it.